Okay, let's go start this morning session about this, especially the Lizzie's David, and David is going to talk on this nice presentation about Taurus-Auriga, this.
Right, so this reminds me of the first years of observing. All right, so this is a journey that actually starts with fall, but we'll get to that in a moment. Just by way of introduction, the general topic here is observational planet formation, and the motivation is that the basic properties of planets, their masses, their orbital architectures, their compositions, are largely determined in a very brief formation phase in the disks around their stars. And the method that we're going to use is to empirically characterize the properties of these disks using radio interferometry to measure the cool dust and gas. And in doing this, we're incredibly fortunate that nature provides us with hundreds of young stellar systems relatively nearby, where planets are probably forming now, and we can observe them directly. And of these many hundreds of systems, there's one that really stands out, and that's TW Hydra. Why is TW Hydra important? It's important because it's the closest T-Tauri star. So it's recognized as a classical T-Tauri star and star of the disk in the early 80s, but it was strange because it was far from any dark cloud. There was no star-forming region nearby. And it was kind of a curiosity. And then there was an important observation in the mid-90s by Ben Zuckerman that it showed CO. There was a very narrow 1 kilometer per second wide CO line. But it was also kind of odd. One possible interpretation was that indeed it has a gas-rich circumstellar disk, but it's viewed face on. And the key thing that happened in 1997 was the Hipparchus mission released a distance to TW Hydra. It was only 56 parsecs away. So it was 2 to 3 times closer than any other T-Tauri star. And this led to just an explosion of interest in this object. Now, it's located in the southern sky. It's at minus 34 degrees. Actually, minus 34 3/4 degrees, which turns out to matter through some telescopes. So it's hard to observe with the millimeter interferometers that are all located in the northern hemisphere, if not impossible. But one interferometer actually could observe it, and that's the DLA. And so when I arrived at the CFA, Luis Rodriguez, one of Paul's close collaborators, was upgrading the DLA with new receivers for a 7 millimeter wavelength with the express goal of observing dust in disks surrounding stars. And Paul connected me with him, and we had a very, I'd say, fruitful collaboration, largely starting on sources in Taurus. And here's a picture of Luis from one of our observing runs in New Mexico in 1997. And about half the antennas were equipped, and then I learned about TW Hydra. But I was sad because we missed the opportunity to propose to observe it. So these observations could really only be done at nighttime in the winter when conditions would be best, and it would be 2 or maybe 4 years before we had another chance for the VLA to be in the right configuration for winter night observing. And I went to Paul and I said, "Isn't this tragic?" And Paul said, "What?" He said, "You should just write to Mary Clark, the scheduler for VLA, and say you need the time." So that's what I did, and we got the time. All right, and so we made these, these kind of amazing images actually, which probe the dust distribution on scales of 5 to 50 AU, which was really quite revolutionary at the time. And the power law distribution between those radii actually is held up to this day. Okay. We made other early attempts to image TW Hydra. We went to Nobiyama. Here's Paul at Nobiyama. Here's Paul at Nobiyama. That got weathered out. It probably wouldn't have worked anyway. It was a little too far south. We went to Australia. They had 3 antennas with 3 narrowband 3 millimeter receivers. And we were able to get these kind of nice results. We actually detected and resolved the HCO +1 to 0 line, which led to a collaboration with Amin Van Bishop and her students to to show that resolved molecular line observations could actually constrain chemical models of this. Okay. There was another odd outcome. In those first observations of the VLA, we only had half the antennas at 7 millimeters. So we used the other half of the antennas at 3.5 centimeters. But I didn't really expect to detect anything because there had been an earlier observation that had just an upper limit. But strangely, to me at the time, we actually detected TW Hydra at 3.5 centimeters. And I thought, oh, it's varying. This must be some non-thermal stellar activity. Maybe we could observe it with the VLPA. So I put in a proposal with Mark Clausen to monitor TW Hydra with the VLA just to see how bright it is. And it never changed. So that was like the worst variability proposal ever. But then we followed that up with longer baseline observations that showed it was resolved with the VLA, and then had a steep spectrum to long wavelengths. And in fact, the 3.5 centimeter emission we were observing was dust, very large grains that are still an unusual observation today. Okay, then time for the SMA. So I was excited. TW Hydra. We're now far enough south in Hawaii we could actually image it with a real millimeter interferometer. And this was a high priority early science target. We had 5 antennas barely working, 2002, Yoshi remembers very well. And we were able to resolve the CO line both spatially and spectrally, and thanks to modeling from Charlie Chi, could really show that this was a disk in Keplerian rotation, viewed with an inclination of just 6 or 7 degrees. Okay. So as the SMA capabilities increased, we did more and more with the SMA. Here's one of my favorites. This was a search for turbulence with my student Meredith Hughes. Turbulence is invoked in planet formation for all kinds of reasons, for mediating angular momentum transport through the magnetar rotational instability, to grow grains, to make planetesimals, to migrate planets. Turbulence is very important. And we were able to put a pretty stringent upper limit at about 10% of the sound speed from these very high spectral resolution observations with the SMA. That was fun. We also tried dust polarization. So you heard a lot about this yesterday. We thought maybe we could see magnetically aligned grains. Well, the bottom row here shows, the bottom row here shows the data. Very high signal to noise Stokes I, nothing in Stokes Q and U, so just an upper limit, but less than 1%. This was inconsistent with popular models at the time for magnetic range alignment of disks. Looking back at that paper, we made a very lengthy argument about why cell scattering wouldn't be important, and now we know that that's actually what was nominated and why we didn't detect anything. Okay. And then at the limits of the SMA, here we have kind of our best SMA data. Beautiful, oops, do that again. Beautiful continuum map. You can see in the visibility function it ringing. That's the sharp edge of the millimeter dust at about 60 AU, whereas the CO extends out for hundreds of AU. And this was really great evidence for the drift of large grains through the disk. Really, I think the first conclusive evidence for that, which was led by Sean Andrews, who was at the CFA at the time. But of course, included Paul. All right. Then TW Hydra was a high priority target for ALMA, science verification. So we didn't have either the spatial or the spectral resolution of the SMA, but a lot more sensitivity. And this pulled out some line wings in the CO that were difficult to explain, or actually easy to explain like anything else, but we didn't really know. So Sean's student, Catherine Rosenfeld, led this effort. And we thought of lots of different ways how to get these bright line wings. The one we didn't think of was pressure broadening, which actually may be the solution. Okay. And then finally, for ALMA, got the long baselines, beam sizes of 20 milliarc seconds. That's just 1 AU at TW Hydra. And again, Sean and I led this long baseline observation, and you can see this the beautiful rings and gaps in TW Hydra that were revealed by ALMA. I will say though, these are actually quite subtle features. I mean, they're just sort of 5 to 20% dips. They're not they're not 100% contrast features like in HL tau. And if you put GW Hydra at Taurus distance, you actually wouldn't see many of these. You would only see just the, you just see the main one here, and that's it. All right, so this was, Paul, this goes with your kind of qualitatively different data, right? The beam size here is not quite a factor of 1,000, but it's many hundreds times smaller than the SMA. You can really see something different. Okay. Same is true of the lines. We kind of repeated the study that Meredith Hughes did. This was led by Richard Teague, who was an SMA fellow. Rich developed a really clever way to take out the cavalier rotation, look at the velocity residuals, and at the very few percent level, there's some really interesting red and blue shifted stuff happening that may be related to the presence of a planet in the disk. All right, and now we're approaching the limits of ALMA. So much deeper observations, the continuum led by Nagayoshi et al. Revealed this amazing, tiny little feature here that sticks out with a contrast of about a factor of 2. It's just a few AU in size. And this is consistent with the envelope of a planet filling its Hill sphere at that radius. But one really needs the resolution and the sensitivity, right, to pull out this, again, sort of qualitatively new feature. And it's no coincidence, actually, that it's at the edge, because that's where the dust optical depth is finally starting to drop. And so one can see through the disk down to the midplane where a planet like this might be growing in their feet. All right. So what's next? So next, this kind of observation suggests that one really does need to go to longer wavelengths where the dust becomes more transparent to see more of the substructure that may be in the midplane that's more relevant to planet formation. And one would really like to get a few milliarc second resolution to go to sub-AU scales in many disks, but in particular in GW Hydra. But you need extremely high sensitivity if you're going to be looking at low optical depth, cold dust that just has very low brightness. And so this is one of the motivations for the next generation ELA. And one can imagine, making all kinds of beautiful images with tiny little features that are associated with the gravitational influence of planets, even in the terrestrial planet-forming zone of many disks. And what's more, the dynamical timescales there at a few AU are commensurate with graduate students, and so one can make many observations at different epochs and potentially make movies, right? And over the course of some years, watch the features develop and rotate. It really would be amazing. And I have to say, this is not a new idea. 20 years ago already, I wrote about this, in the case for the SKA, right? It was just one needs to go to centimeter wavelengths at high resolution, and we just need to keep pushing that. All right. So, what are the takeaways? TW Hydra at high resolution. Well, it's a southern T Tauri star. It's only 60 parsecs away. And because of that proximity and also the baseline viewing geometry, it's really been a touchstone for a lot of unique studies of this structure and planet formation processes. And so I just made a little bit of a selection of some of the work we've done over the years. I left out all chemistry and all kinds of other things, but it's really been an amazing journey. And first, I need to thank Paul for that very first observation, because I think if I hadn't done that, probably never would have done the rest. And you can see, he appears on all these papers, right? He stuck by it and made very valuable contributions all along the way. So thank you.
Questions?
I can just shout. So David, on the TW Hydra image that's shown a little more, and what is the contrast? Say if it's tilted, would you see it?
Yeah, it's just barely a factor of 2. So, it gets harder and harder as you incline, right? Yeah.
Hey Dave, nice talk. What's TW Hydra doing out there all by itself? Why is it in a cluster with all the other Taurus-Stars?
So I didn't emphasize this point, but it's just a little bit older. So it's in a moving group, and it's probably more like 5 to 10 million years old, and so the cloud has dispersed by now. So then the question is, why does it retain a gas-rich disk for so long, right? So is it just, was it just a late former in that cloud, or does it have some odd special property? This is actually something that keeps me away occasionally, because you think, well, this one's sort of anomalous, and so maybe studying this one so closely isn't a good idea. But I think the answer is it's just probably a bit older and has been a little slower to evolve for some reason.
Okay.
Just one question about TW used to be this, right? But how much do you need to increase the dust to gas ratio until you can get this structure clear like this?
I'm not sure what's their question, Steve?
The dust to gas ratio, because we suspect in nowadays, right? TW could have been depleted in gas, and now it's confirmed to be gas-rich disk. And then how much increase you have to have in the dust to gas ratio to see the structure clear, but we're still gas.
Yeah. So there are a couple of factors that come into play. So one is, first, there's been a lot of dust evolution. So measuring the dust mass is hard in a way. The gas mass is actually reasonably well constrained because there's an HV measurement from Herschel. So the gas to dust ratio is not far from interstellar, probably, in the end.
Okay, let's start again. Now we have ice walls within one.
Okay, hi everybody, good morning. It's very early to me. But my original plan is to talk about the icy walls in Broad form. That means I plan to have this series, Europa and Enceladus. But I found out last night and said, well, it's time is really little. So I guess you know what I mean. But anyway, so I'll focus on Enceladus. I'll let this work. So this is my students, and this is postdoc, and this is Professor Yuan. Okay, so I'll talk about this exosphere and also neutral molecular gas is around this Enceladus. Okay. So Enceladus is known, it's for an active program. I think it's so famous to most people study solar system and don't know that. And so also it's usually have this salty subsurface ocean. So that's why we got interested in Enceladus. It's been there for focus for astrobiology study in the past 20 years, I think. And also it contains some hydrothermal system within this subsurface ocean, which provides energy and organics and for primitive life potential. So the plume, Cassini actually measured in the plume that a lot of molecules there. This many is water ice and those things, and molecular hydrogen, carbon monoxide, and all molecular because they have the same molecular weight, molecular weight. So they cannot separate that. And also carbon dioxide and ammonia, hydrogen cyanide, methane, and formaldehyde, and hydrogen sulfide. So you see. And also the some organics been detected by this mass spectrometer, methanol and ethylene. So this is Herschel and Schwarz's observation of the water. You can see this in the plume. This water and this OH thing is from the plume and escaped to this donut-shaped torus, basically the torus here. So that's why the absorption here. So that's 2011, Ohashi did his famous observation of the torus. The torus thermal is actually the E-ring of the group Saturn. So this picture shows you can see this plume coming out from the southern polar region of Enceladus. This is the shadow of Enceladus. The sun is here. So the plume is actually will contain most of the original material from this supposed from the subsurface ocean, and the torus contains the composition mainly from escaping the plume materials, right? So our goal is actually to find out what kind of molecular composition of this surface ocean. That's in other words, we are trying to find this composition in the plume and the torus. So before the observation, we didn't really know whether these people, whether this molecule will be back. So we went to ALMA to do this observation. Then because Enceladus is very close to Saturn, so to avoid this contamination from Saturn and then make the rings around, so we have to choose very high frequency, so we have a smaller primary beam. Okay. So that we choose band 9, okay, that gives us 9 seconds primary beam, so we can effectively avoid the contamination from Saturn. We actually conducted observation when it was at least 30 seconds away from Saturn. Okay, so this is the somewhere here and here, that's the maximum elongation. Okay. So this is where we have this observation done. Okay. This part, okay, the date written there, and this part. We actually have 5 observations. Actually, we have 7, but 2 of them actually didn't pass this QA2 because the system temperature is too high, over 1,000 degrees. So we didn't accept that. So now first I show you this continued observation with the natural uniform weighting. We can see that we have a clear detected this Enceladus. Remember, Enceladus is only about 500 kilometers in size. Okay? So it's actually angular scale is smaller than 0.08 second, so even smaller than the pixel we use. So you see this is a convolved with this can be. So if we use natural weight with taper, we can actually see some extended emission time. Then we say, well, first we saw this is silos, but we spent a lot of time to try to remove that. And I think it's real because then we put these things to the orbit when we observe. You can see actually trace the ring quite nicely. This is not to scale, okay? Because if we go back to scale, you couldn't see this thing at all. But this is enlarged, but just to show you some, give you some thinking about this. Things we detected is actually kind of traces the E-ring. So this is, so this is the gas we first detected CO. So this is one of our goals, because CO and N2 is hard to separate. So we see a lot of CO there. Okay? And this is clear detection, and this is velocity. This is in the so-called leading hemisphere. Leading hemisphere really means this side, okay? Facing us, we are looking at this way. Then the velocity is redshifted. Okay? So the CO, as I just said, CO is important because we can distinguish it from this molecular nitrogen. Okay? And CO also can be autolysis pulled out the methanol. So if we see CO is not indicated, there's methanol there. Okay? So because it's so close to inserters, so we can probably think to the group, because we don't have this relation to say 100%. So then we have a second detection is sulfur dioxide. Okay? This is also very close to the inserts. Okay, this is, sorry, I forgot to mention, this contour really means the continuum, okay? The 3 sigma and the 8 sigma and the 13 sigma. So this color scale is the SO2 detection. Also the scale here is 0.8 arcsecond, 0.8 arcsecond. So it's really zooming into the region. Okay? So this is a line, and also this is a leading side, so the velocity is also very shifted with respect to inserters. So with the detection SO2, it's really applied this hydrothermal system, and this, previously is indirect evidence. Ours is also indirect, but kind of as a coping evidence for this hydrothermal system. So because of the hydrothermal system there, so we expect sulfur in the subsurface ocean. Then, okay, hydrogen cyanide. This one is particularly interesting because hydrogen cyanide is very important to life. It can kill you, but it's very important for life. So we have this ground state detection at CN87. The frequency pretty high, it's 708 gigahertz. And we have the nearby there is another vibration of hydrogen cyanide. We could detect that, but you cannot use this low energy level. Upper energy level is very high, so over almost 1200 K. So but we have this side detecting the trailing side. That's the other side. The velocity is shifted. So we put these two map overlap to each other. You can see the identical position, but not quite. Okay, maybe that due to the excitation difference. And may have different mechanism. Okay. So the profile is pretty similar. The spectral profile is very similar. Okay, so and since we suspected to present in the plume, but that's from the IMS mass spectrometer data. So it's not confirmed. So we actually see this hydrogen cyanide as great. And I just say it's a very important species to this ocean chemistry. Okay. And this is probably this low vibrational HCN could be due to the impact of electron impact and ion impact. So here it is enough energy to excite. So the next one is methanol. A lot of people are very interested in methanol because it's methanol in the ocean. That's really the indication of this organic things in the ocean. So again, we have this detected, but this is you can see there is a strange range share. We actually try to see this from side level. We try a lot. We just like point for people to do this. We have masks and erase masks and trying a lot of things different way and boxes and everything. But it stayed there. So it's probably real. Very likely it's real. And this is from this trading side. Again, this is velocity is negative. Maybe it's a cruise ship to velocity. So the maximum, as I said previously about CO, so you could even produce CO. So if we see CO, we expect that if it's from the UV photolysis, then we expect we will see from maximum, right? To that's one thing. So we actually see that. We see this near very close to Enceladus. But then there's another way, because to explain this ring-shaped torus gas, torus-like gas, then we need other chemistry to produce them. This could be due to this photochemistry of this methane and water in the ice, so the ice is released into the space, and so they come out there. And also it could be gas-phase reaction from this C3 ion and H2O. So that's why we can have that produced at a large distance from Enceladus. So how much time I have? Okay, it's 2 minutes. Okay, so maybe okay, 2 minutes ago. Yeah, because the water is very difficult to explain. This year, this JWST, the water detector, right? So outgassing water from Enceladus. And so we also see that with this contour, the contour here shows continuous. I just showed this to you before, right, previously. So this is the continuous. So we overlap this region with this water emission. But it's very hard to really pinpoint where the water is. It's kind of like everywhere. And again, it's like noise. I mean, it's everywhere. But it's only happened to this state, okay, the particular state. We didn't see that on other dates. So that's why we try to see if this is real or not. So we actually we are averaging all this flux over the entire image. You can see that this stand out very sharply, just one channel stand out. I mean, this is exactly where we would think the water will be. But it's actually there's a terrestrial ozone is here. So that's like a 4 kilometer separation. Yeah, but the velocity is different, that's for sure. So this is really strange. I mean, not strange, but surprising. Yeah. So the water actually related to gas torus, right? So it's everywhere, right? This actually see the continuous images, we can get a hint. So the water definitely is from the plume, then from the E-ring, that's part of the E-ring. But the excitation is very high. Yeah, I forgot to really mention that. The excitation is 2360 K. Yeah. So it's very high. So that's why we don't see that in our terrestrial atmosphere. So we don't have this absorption there. But anyway, that's probably due to the same mechanism as this hydrogen cyanide vibrational hydrogen cyanide. That's probably due to this electron and ion impact. So finally, the summary. So we detect all these molecules, and some of them link to the plume. Entity conclusion, but the methanol is probably both Taurus and plume from different mechanisms, chemistry reaction. Okay. So we also found leading size always has a redshift to the velocity, and the trailing side is blue shift to velocity. So we think that's probably due to this sort of subcapillary rotation of the Taurus. The Taurus. So that's always fall behind. So that's why we have this velocity shift. Okay. That's my talk. Thank you.
Thank you.
time for 2 questions.
Thank you. Can you compare anything about the Enceladus plumes to the Europa plumes? Are they similar?
Europa plume is not actually confirmed by detection. So we actually try to confirm that. Yeah. No one really see the plume from Europa so far. But yeah, those that trends in this trends in HST, trends in detection is that get also debate. So we hope we will be the first one to detect the plume from the real plume. I know there's a lot of people doing this, right? It's tech, right?
Okay. So another question over there.
Do you know roughly what's the lifetime of this plume? The lifetime.
Lifetime of the plume? No, we have no way to know because we only have 5 observations, right? Some, actually, it's difficult. I think the plume is coming up continuously. So just those molecules, whether it be there all the time or not, it's hard to say. The plume itself is always there.
Great. Nice to thank you again.
Okay.
The next attention is Nagayoshi Ohashi from Indies around Protostars.
Right.
Thank you.
Thank you. So let's see. All right. Okay, so I'm gonna talk about the disks. Well, actually, David gave a very nice talk. The disks are the Taurus source, but I'm talking about the disks around the Protostars. And I want to use this opportunity to look back, how my research has been developed as angular resolution actually improved. And how to Okay, but before I start talking about the disks and protostars, let me talk about let me show you the Taurus star disks, because as you know that at higher resolution, disks I actually have so tremendous images, and this is actually the one we took about the 30 years ago using the Nobel millimeter interferometer at 3 millimeter, and the resolution was about 4 arcsecond, and what we see is just a block. Of course, we can resolve the image structures with this resolution, and then later, this is a one observed tiny disks by the ALMA. And then let me enlarge. This is the one you can see this one many times already. But anyway, in terms of the resolution, this is 50 times higher resolution. And also in terms of sensitivity, this is more than 100 times better sensitivity. So that can makes a big difference, showing such tremendous images. Now, so this is the diagram. I was just checking what the resolution I was using in my research, and this is a diagram showing how angular resolution changing as a function of time. And early days, actually before 2000, something like 14, when ALMA started, my resolution I have is more like more than 1 arcsecond always. And then after 2014, it's getting lower, and eventually, we achieved something like 0.04 arcsecond. And but based on my experience, early resolution more than 1 nanosecond, what we see is that mostly are infloring envelope. Okay. Well, you need to know that of course the protostars are embedded in infloring envelope. So that even at the 1 nanosecond resolution, we still see that most of the things we see is infloring envelope. And then less than 1 nanosecond, but more than 0.1 nanosecond, we start seeing disks. But still together with the infloring envelopes. And only when we go to something more less than 0.1 nanosecond resolution, we actually start seeing the disks more. The disks are protostars more. And this is one good example showing such an evolution according to the angular resolution development. So IRAS 04368 plus 2557. So this, when I was observed, this was more like 25 years ago. This was just one of the protostars, or just one of the IRAS sources in Taurus. And most of people didn't really pay attention. But of course, this is the latest image of the ZWST, and then this becomes, of course, more popular now. Everybody now knows. And we observed this guy about 25 years ago, this region. Okay? And this is all right. So this is the image we got using ALMA in CMTO. Not 2 to 1, sorry. That's supposed to be 1 to 0. Supposed to be 1 to 0. And the resolution is something like 5 or 6 something. And the people are showing the integrated intensity map of CMTO 1 to 0. And you see some sort of elongated structure with the scale of 2000 AU. And when we, by the way, this is one of the paper I was working with Paul. And when we look at the velocity structures, cutting this major axis of the elongation. This is a position velocity diagram, right? And then there is a velocity gradient from north to south, like this. But not only rotation, such a velocity gradient. We see the more emission like here and here as well. And in order for us to explain such a velocity structures, we need to have a model of infloring and rotating envelope. And this here, if you just assume the Keplerian motion, pure rotation, then of course we can explain the entire velocity structures. Right? So then basically at this kind of resolution, we cannot see the disks at all. What we see is infloring and then rotating envelope. Now, later, something like 15 years later, we want we start saying that we have start thinking of whether we can see the Keplerian disks around the protostars. Then we came back to start observing this guy using the ALMA, SMA, and this is the one we got from Masayuki, Yi-Jehng, and myself, and Paul together. And this time we observed CNA 221, and this is the resolution, something as 3-axis resolution. And again, we checked the velocity structures, actually rotation curve along the elongated structures, and then this is what we got. Radius, rotation velocity, and we measure the power of the velocity, rotation velocity as a function of radius, and what we got is the power is about 1, meaning that this is not Keplerian, but still rotation, conserving the angular momentum. So again, what we see still this resolution. What we see is unfortunately not Keplerian disk, but still infloring envelope. Right. So in order for us to see even more higher resolution, of course, we have to go to ALMA. Alright, so then now we look at the even tinier region with the ALMA, And this is the image we got, with our material as estimated to be one, but less than 1 maximum distribution. Then, as we did, we measured the rotation curve around the major axis of the elongation. And then this is what we got, again, the radius and the velocity, rotation velocity. And when we look at the rotation curve very carefully, we found that at the inner part of the rotation, it seems to be close to the Kepler area. Now, although outside is still showing the rotation, conserving angular momentum. But of course, not many people convinced, oh, okay, this is just whatever things, right? So of course, we keep observing, and then this is a better version. I later, including my student, Aso-san, we got this one, simulated tutorial, and this is the rotation curve. And again, in a part for rotation, is a Kepler area. Now I believe in what everybody said, okay, we are starting the Kepler area rotation. All right. So then now those are the molecular gas. Then the question is, of course, what's happening with dust disks, particularly like HL tau. Interesting question is whether we can see any substructures in the dust disks and the protostars, and whether there is any sign of the early planet formation and the protostars. That is a question, right? Now, so we start also looking at the dust disks and protostars, but even higher resolution. So that's the one. The ALMA project, so-called E-disk, and with this large project, we observed 12 plus 7 and 7 plus 1 protostars at the angular resolution over 0.04 axial resolution, which is the highest angular resolution which I had so far. And then I have two important goals, but one important goal is, of course, searching the substructures, searching for the substructures in the disks around protostars. All right. So then this is the images we got. 17, 19 sources in total, and you see the many elongated structures, and you can tell all the disk structures mostly resolved. And let me compare with the F15 to 27 disks. This is the one we got early days with the Noveana at the 2.7 millimeter, 2.7 millimeter continuum, and then this is the ALMA E-disk image. Now you see how much difference, and with the ALMA, of course, structures much more resolved. Right? So I don't have much time, so I cannot really go through too many details. But for example, when we look at those images, you can easily tell that how big is the size diversity, for example. Right? There is such a big, whether this gallery is showing all the images with the same linear scale, so that you can tell some of disk showing a very large structures. On the other hand, this there's a tiny disk here as well. So then, when we look at the measure the size of the continuum, then we can see the two order magnitude different. So again, there's a big size diversity. And also, some of my disks showing a very high brightness temperature, which cannot explain as a passive disk. So we do need to include the accretion shock, accretion heating to explain such a high temperature. And now Shige is, I think, almost ready to submit a paper. All right, but anyway, in order for me to show some more details, let me show you the enlarged version of the gallery. And again, same but enlarged. Okay, and then I also show the disks in the order of the volume temperature. So this is the lowest volume temperature, supposed to be youngest, And this is the highest for temperature source, supposed to be the oldest. And now, when you look at here carefully, you can tell that those two disks shows the substructures, like a ring substructures. Okay, but not most of other sources is not really showing such substructures. Okay, could be this guy, but anyway, all right. But then at the same time, when you look at here, brightness asymmetry, we can find also brightness asymmetry along as I showing this white the line. You can see the brightness asymmetry along the minor axis of the disks. Okay, so those two characteristics, relatively few distinct substructures, and also the brightness asymmetry, particularly along the minor axis. Those two characteristics are quite different from disks, Taurus-Stars. And then this is the comparison between the E disk sample and the D-sharp Taurus disks done by the Chunhua at the similar angle resolution of 0.04 axial resolution. Again, it is doesn't really show the distinct substructures. On the other hand, many of disks are showing brightness asymmetry, particularly along the minor axis, and that could tell us that this seems to be a more flare up, but a substructure is not really formed yet. All right. So I don't have much time, so then I need to wrap up. So basically, my research in the last 30 years, angle resolutions, I developed something like a 2-order magnitude, and now I can start seeing disks. Eventually, I start seeing disks on the protostars. So such a sense, I study of the disks on the protostars just started. So further investigation has to be done. So please stay tuned. Thank you very much.
Thank you. Is there any question? Okay.
Nagayoshi, nice talk. So I have a question about these files. So this is one of the sources that has always been this discussion about why it has a disk or not. So are you confirming that it has a disk and it is incremental?
Well, in terms of kinematics, kinematically, as far as I know, we haven't detected the Kepler motion yet. Is that right, Sue?
Right.
Yes. Okay. Yeah. So we do need a very high, even higher resolution, or maybe even higher sensitivity as well to see the motion. And of course, this thing is, we can see a lot of absorption because of the dust continuum in the part. That's the observation.
Another question? Let me ask you something. You are planning to do the same experiment and measure the velocities for all of these?
Yeah. I wish I have enough time, but you have a CMATO or whatever other lines for all the sources. So we are also checking the Keplerian motion diagnosis, and as far as I know, most of them, not everything, everybody, but most of them showing more or less Keplerian motion. Although difference between the Keplerian and ALMA is very tiny, so sometimes not easy to do the distinguish.
Okay, thank you. This question is and this is a really fabulous system that is teaching out.
Good morning, everyone. It's me again. So now I'm going to present my journey with Paul in one slide to show how I started with the polarization studies since my PhD thesis. So in one page, that's the work we have done with Paul with the SMA. Since 2005 or 6, we started to write the proposals. So these are the four favorite objects When I started, and we proposed, why not look at the PhD thesis of Peter Solomons, and that time he's about to finish. So we look at that, and I pick at the ones I think may be relatively simpler, and we might have a good detection with the SMA. So we have looked at this W51E2EA region, Patrick's talk, where we see a coalescing force, which seems to drag the magnetic field, shown in red. We observed with the SMA, which shows the B field can be dragged in, influenced by the gravitational info toward E2 and E8 cores. And another region we observed together is W54, another coalescing core is located here, and we have some twisted B fields, which is, seems to looks very similar to what we have seen with ARAS 4A. We also look at the more evolved regions, G5.89 and Orangian KO. In G5, at that time, we know there is a very energetic H2, ultra-compact H2 region here. We estimated the energy budget, and we realized the B fields could be shaped by the stellar feedback here with H2 region. In Orangian KO, it's even more complicated. We know at that time already there's an explosive outflows, which all point to this spiral region. We look at the B fields, which all look at the symmetries, and we trace back to a location. All these B fields point back to this. All this suggests that all the B field lines at these locations, they could be influenced by stellar feedback already as time goes by like ultra-compact region or explosive outflows. They could also be magnetically aligned. In BNKL, for example, we rule out this possibility because even though there's an explosive outflow, the polarization pattern will be more close to toroidal, and is perpendicular to the explosive outflow direction, so it's in contradiction with what people would expect. So since then, I realized it's so complicated, the polarization in high mass region. So I thought of, okay, why not look at another topic I'm also interested, which is a more cleaner region in disk, circumstellar disk. So then I started to work, write a few papers, start to look in, work in parallel on disk, for example, in the digital A system. And so I'm going to present the ALMA results I published, I've done in the past few years. From ALMA, we have seen quite a few polarization surveys in circumstellar disk. This is a few survey in the young stellar, young stellar objects. You see the polarization has all kind of pattern. About 40% of the surveyed objects has a polarization detection, and about 60% of these are inclined. The inclination is larger than 60 degrees, and in this disk, the polarization pattern is more parallel to the minor axis. So the rest 30% of the detected objects, you have a also polarization pattern, something like this. For example, this one and this one. So, and at that time, before that, since the first year of ALMA observation, we already know, first few years, we already know that the polarization from circumstellar disk probably not tracing the magnetic fields. The reason is that in the observed polarization pattern, you see that there is a radio-like polarization pattern at smaller radius, and at some point there will be a flip in polarization angle. So this is more can be explained with the cell scattering mechanism. So it's due to the radiation from the dust flame being scattered by the thermal emission by the dust flame is scattered, and depending on which angle, depending on the observer and the inclination of the objects, the polarization pattern will vary a lot. And this object seems to can be explained more or less with this cell scattering model. This is famous HD 142526. So when at the time we start to, I work at the digital age system, it's bright enough, and I thought, okay, why not we look at this to see if we can detect polarization and what's original this polarization pattern. So we managed to get the ALMA data in cycle 6 with 2 band 3 millimeter and 0.9 millimeter. So you have good detection at the near the center is around it's a circumstellar disk in one of the disks, and there's a very sharp ring at the large radius. Okay, so this system, just keep in mind, is now it's quadruple system with at least 4 stars inside this circumstellar ring. So one of the continuing peak at the center of the ring is associated with the central star. And between the circumstellar disk and the dust ring, there are some mercury gas and also very small dust rings. So these are the results. Look like at 3 millimeter, we have the polarization pattern is more or less very close to azimuthal, and at 0.9 millimeter, you have a azimuthal pattern polarization, and the larger radius is flipped to azimuthal, and this outside is a radial-like. So this, if you look at the image at that time, okay, maybe it's purely due to cell scattering. So we might be able to test the dust grain size, etc. at the time. And then we realized, okay, we look into the detail of this polarization is not that simple. Because first we look at the polarization at the circumstellar disk, where at the 3 millimeter and at 0.9 millimeter, they are all more or less tracing parallel to the jet direction. So, that's the polarization here. I don't know what's the relation with jet, but it's in the same about the same direction. But the polarization pattern on the dust stream itself is quite peculiar. So what we did is look at this image. I realized just by you can tell it's not purely symmetrical, and some systematic deviation from the azimuthal direction. So in red is I show the detected polarization, and in cyan is the expected azimuthal angle at that location. And then we calculate the angle difference at the location where we have detections. All of them are in a right sense, they are in the same direction, more shifted to this direction. And the rotation is counterclockwise. So this deviation is detected everywhere in most of the detected position, and it's systematic. So here shows the distribution plot, angle difference, the number. 0 is here, so the difference is about 0.9 degree from the azimuthal direction at 3 millimeter. Similar pattern has been seen at the 0.9 millimeter data as well. But here we keep in mind the smaller radius is more or less radial-like polarization. So we only look at the data with the larger radius. where the angle difference is plotted here. Also, most of the points is in the right sense as what we have seen in 3 meter. And here shows the distribution plots. The systematic deviation is also minus 8 degrees. So we, in 3 meter and 1.3 millimeter, we see a systematic equalization angle. And this seems robust if you take into account of the data points we have detected and weighted with the uncertainty and the intensity, etc. So the uncertainty is quite robust, minus 8 degrees, plus minus 1 degree, something like that. So then the question is, so what could be this origin of this deviation? From the alignments of the detection at the circumstellar disk and with the jet, we know it probably some physical origin, and we have checked. Actually, there is no observational systematic error in this data because the detected causation in the calibration is consistent with what we know in archive. So the origin, okay, so if we interpret this as self-scattering, you cannot reproduce this kind of deviation of causation pattern. So although with this model we can reproduce the causation percentage at the 0.9 at one of the wavelength, but doesn't match in the other wavelengths. If you look at there's a new model proposed by Yi-Jehng that if the dust grains are aligned with magnetic field, but in a near regime, which can also reproduce this kind of blades causation pattern, but none of these two mechanisms can reproduce the deviation of minus 8 degrees. So we need something else. Okay, so this gold mechanism, we know if it's due to mechanical alignment, if your dust is located, it can, if the causation pattern will align with the flow direction. So what if this purely gold mechanism, if there is no radial drift in the disk, then you would expect the causation pattern also purely atmospheric. So in order to have a deviation, there's a mechanism proposed by Katoka in, where is the reference? Okay. He proposed there's due to the helix he had some systematic deviation, which he observed with his team toward the AS209. But in that mechanism, if you consider the helix property of the dust grains, actually the rotation sense is in contradiction with what we know about this object, and also with GG house, so that mechanism doesn't work. So what's left? So we look into two possible reasons. One is if you have a radial drift. We know the radial drift velocity is about 10% of the, about 5% of the capillary velocity theoretically. But what if you take into account if you from the station you take the deviation of the angle from the angle minus 8 degrees, which will require 40%. Or if you take into account the inclination angle of the object is about 12% of you will require 12% of the radial direction in order to create this kind of violation pattern. So it's much larger, a factor of 2.5 larger than what the theorists would expect. So this could be, but with some just theorists need to come up with a different model. The last possibility is that can these dust grains aligned with the spirals? In topological systems, two kinds of spirals has been observed. One is with the infrared interpolation stabilization lights, which are marked in the white arcs here. So you have some spiral patterns here. And in that paper, Kepler paper, they thought this might be due to tidal interactions of the objects and enclosed objects, which create this kind of curvature. Another spiral pattern is a much larger scale from trace with CO line. It's starting from this outer part and going out. So all these are in the same, in the right sense, they are all trading spirals. So can the detected polarization be aligned with these spirals? It could be. So that in this case, then we will require the spirals here cannot be a pattern, like just a stellar pattern like what we have seen in the galaxy. It could not be like that. It's something else. So in short, so this is an overlay of the polarization, detected polarization at 3 millimeter, overlay on the spiral pattern. Seems matches well by. So in summary, we see peculiar polarization pattern which shows a systematic deviation of -8 degrees from azimuthal pattern. So we would need the radial drift velocity, at least 2.5 of what expected in order to reproduce this kind of pattern, or the dust grains are being aligned with the spirals. So, or both. So we will need something else in order to explain this polarization pattern. And I'm looking through the literature and also looking to analyze more, but actually there are only 2 objects has been detected this kind of pattern. So more high resolution data, this analysis needs to be applied to this polarization data. So I stop here.
Okay, thank you. Questions? A question, I didn't see the magnetic field from the inner source. Will the magnetic field also change when you change in frequency and the direction of the inner object?
Yes, what I show are all polarization data. This one, the 0.9 millimeter data is more noisier. So if you take the mean, is the difference maybe is consistent within the uncertainty.
Okay.
Yes.
There's no change.
Yeah, because the uncertainty is about single detection is about 5 degree, 8 degree.
Yeah, very impressive. Really nice.
Yeah, yes.
Thank you. Thank you. Charlie Chi. Well, I'm not really asking questions anymore. I mean, I know you from a long time ago, and you always ask questions, but now you are really shy. You really now are retired also from asking questions.
Good morning. So today I'm going to talk about the probing the CO result in disks. CO is the first molecules we detect in the disks with the radio telescope. Here is an example of what we observed with the ASIAA on Taurus-Auriga, which David mentioned the closest, what Taurus at the disk around Hercules, actually 16.396. And the interferometry shows you beautiful apparent rotation around the stars. And you can determine the disk properties like the position angle, inclination, and how big the size of the disk. Right? That's exactly the first research we did with the SMA. And this is the first paper I wrote with Paul and David back in 2004, that's 20 years ago, in the special issue of the APJ dedicated to the ASIAA's early science about the imaging disk around hydrogen. Now I revisit the parameters used for simulating hydro, and of course there are still many unknowns. But one parameter's inclination angle is stand to the test for today, that we determined at 7 degrees plus or minus 1 degrees. At that time, I suppose that I was very proud of myself getting such a constrained inclination. And Paul asked, "Oh, you shouldn't give uncertainty on the inclination, but sign line, because you want to know the physical meaning of the errors." It's a kind of very good comments about that. But here is something Paul not satisfied, is the depletion factor due to the CO freeze out, how much the iron is depleted in the disks. And this is not actually crucial for this paper because all the lines are optic. You probably don't know much about how depleted the CO because of freeze out. But this question sent me into a rabbit hole of investigating the CO freeze out, how much it freeze out in the disk in the next 10 years, and even now. So why do we care? We care about that this is the Protoplanetary disk structure. The main thing you notice is the temperature structure, that temperature decrease away from the stars, that you will have a series of the snow lines for over the wall times. The snow lines is what temperature is decreasing, and then until that reach the point where the volatiles freeze out on the dust grains. So you have a series of the water snow line, CO2, and CO snow line along the disk, right? And we know the disk is the site of planet formation, so where the planet formed relative to those snow lines, which will constrain their composition, right? The carbon oxygen ratios, such things. So we are curious about whether we actually can probe the CO freeze out, right? And whether we can determine the CO snow locations. Well, if you remember, I showed you the big disks over that. Did you see any CO freeze out? You don't, because the CO is so large that accompany you, and you wouldn't believe the edge of the CO will be the CO freeze out, because that's just too cold. And so what's going on? The reason to really probe in the CO freeze out, to locate the CO snow line, so one of the way of determining it is using CO itself, but to see whether there are CO abundance drops around the CO snow lines. And the other way is that using so-called chemical imaging, is that searching for the tracers, which is very sensitive to the CO freeze out. And today I'm just mainly concentrating on locating the CO snow lines using CO itself. The reason why we see the CO far out, because its temperature structure, temperature decrease not just radiated away from the disk, from the star, but vertical toward the disk midline. So around 20 Kelvin, that you have an envelope of CO across the whole region that you observe with optic CO lines. But there's away from the stars, things over here, CO is frozen down, that blocking the views of that CO freeze out. Then you need other tracers. Tracers, of course, still relying on the CO isotopologues, because on the surface you see the CO lines, but the isotopologues probably can probe much better about the CO freeze out. That's exactly what we did with the SMA. We had after the early science, we decided to go a lot of times on the multiple CO transitions, CO 2 to 1, 2 to 6 to 5, and to pin down the temperature structure of the disk. Then we use the isotopologs to find out how exactly where CO fits down. Right? So, as I said, this is the contours of the disk vertical structure and the non-density structure. We use the CO geometric transition to determine the temperature structure. Then, for using 13 CO, which at that time we think is thinner, and of course we have the quality of data is so good that we actually can use the visibility film to determine the 3D structure of 2D structure, which is the radius and the height. So we assume CO is photodissociated at the surface, but freeze out at the midline. Then we can actually determine the CO distribution to be in a way that this shaded area is where we determine the CO, and this is where the freeze out location. And at the same time, of course, you can determine this so-called CO snow lines. At that time, we determined 160 U for that. But remember, this is only determined based on 13 CO2. And there's one thing that that's what leading to this discussion is that I assume the deviation factor was set to 10 to the 8th, which is that you immediately disappear the CO. Once it is crossed over this 20 Kelvin, it will disappear. Nothing there. And but you can immediately sense the problem of this problem will come back, because now we have ALMA at that time, the science verification data. Once we have this 13 CO2 this model, then we can predict what the C-dating will to one. When I compare with the scientific verification data, I suddenly realize there's too much material inside, and there's so much. This is the residual comparing the model and data, and there's just too much in this overprediction in the middle and underprediction outside. The reason is that I suddenly realized that I need to modify the depletion factors that doesn't allow it to completely deplete. Then I can determine that another CO distribution, which is pushing the CO zone line to 90 AU, and it is not jumping too fast. And it's actually, when I determine that, depletion factor is actually 5. And this CO zone line at 90 AU in this is confirmed with the chemical imaging that we use N2H plus 32. And it also gives you a ring of in edges around 90 AU, and that's confirmed that we indeed is consistent with our C-dating analysis. But the red line is 90 AU, and the dotted line is previously determined with the 13 CO. So the question is, this depletion factor, if you stare long enough with these things, you realize that these things is actually really determined based on the data. But this thing, how much it jumped, you don't know much, because it's not the figure area. So this is really, this depletion factor is really model dependent. Well, there's another way to look into the disk, actually determining these factors based on channel maps of disk. Here is just a demonstration that those channel maps is based on the resolving disks, especially based on the project emissions on the disk. And this is how we actually determine how the emissions change with the inclination, and change with the orientation, the angle, and also how much material inside of the disk, including how we look into the freeze-out effect, right? So, and the Rosenfeld when they look at CO2 in HD synthesis, they realize that we actually really looking at the Taurus one surface of the front and the back of the side of the disk. And what's inside? This is the first time we really got signature of the vertical temperature gradients. You see that freeze out is actually between these two those things. And but the problem for this thing is that the CO2 is still optic. You probably won't be able to determine the depletion factors based on this kind of observation. What you really need is a very long integration on optic thinner isotopic optics in order and higher resolution in order to determine the fraction the depletion factor. So I am supposed to stop the story stop right now, but we are waiting for more data. And here is a few months ago the PI of this ALMA large program ALMA HT sent me an image of HD sequence C1801, just observed many hours of this things. And this shocked me that you actually now you see the separation of the front and back, but you now see the gap between them. And if I do the simulation with the C1801, use my old model, right? You get this, but if you increase the depletion factor by 100, then you're starting to see the separation. Then back and forth, front of the disk. This is crazy. This to me, that's getting into the high resolution, high sensitivity, optic thinner isotopes are really the key things to determine this so obscure things as depletion by 5, depletion by 300, you're starting to see the difference. All right. So the future, of course, we need to go to optic thinner probes, and we need to go to higher resolution. This is the NGBRA actually provide. This is my example of C700120. The trick is that you need to find out the depletion factors at how much it dropped, right? Because the freeze out scatter. So either that this thing you need to so optic thinner, the abundance is lower than Taurus 1 is not optic thick for this part of the thing. Then you have to still be able to determine this tenuous freeze out area, the detection limit of 10 hours of NGBRA. And then you can safely say you can derive the true depletion factor of the CO without this NGBRA. To summarize, so while you're here, before we know the disk mass using CO tracers, we need to understand the freeze out. And I didn't have time to explain the chemistry involved with the CO freeze out. You still, when CO freeze out, all the chemistry related to have species class and H class and H2CO. How do we know? Of course, with this story, so we need higher resolution, higher sensitivity, optic thinner tracers like C700120 lines, which will be available for the future NGBRA. And I just want to later thanks Paul for the stimulus questions, the things that you asked a question dragged me to many years of thinking. Why is that? Thank you.
Question, Nagayoshi?
So I was just wondering, you know, the latest map from ALMA, so patchy structure.
It's very major things. Just
What's that? And is it real? And what's that?
it's a noise. Oh, the very patchy.
Yeah.
They send me very crappy.
What's that?
It's not very well.
But it's real. Not because of just high resolution.
the grainy things.
Yeah.
That's the noise.
Yeah. Yeah. Well, anyway, you don't know anything.
The second question.
Charlie, I just have a naive question. You may not know, or it's okay, but so when you see your freeze out, is there any way you can cross-check whether your answer makes sense? In the sense that it's not that I don't believe you, but I'm saying, do you have any other molecules or other process you can cross-check with your freeze out? That's my naive question.
Yeah, that's exactly before we don't have sensitivity, we don't have resolution, we don't have sensitivity almost to observe the CO isotope loss. We're relying on chemical tracers, N2H class, which is very sensitive on the CO freeze out. When CO freeze out, N2H class immediately pop up. That's where we see a raining of N2H class. This is how we determine the CO stone lines in this way. And the DCO class itself, although it is more complicated, because DCO class is a problem with the deuterium chemistry, with the not about how much CO is there. It's also about how cold the temperature is. So yeah, but N2H class appears to be very good chaser.
Let me tell you one anecdote from Charlie and Paul. When I was actually just arriving to the CPA for working with ASIAA, I remember Paul started to say I need to really calibrate data from the ASIAA, and I started to do it, and he told me, you should look for Charlie Chi. Charlie Chi, okay, I should go because he's the expert in this program of reducing the data that's in here. And I remember, okay, I should go with Charlie and look for Charlie. And then at some point I arrived to other Charlie that was in charge of the web page, and he actually said, I am not the correct Charlie, okay, and this guy is not Charlie. And then I actually go back to my office and start to look in the web page, who is this Charlie, to go and reduce the data, and then look in the web page. Not Charlie, Charlie Key, and then no, it's not there. And they started to figure out that the name was the Chinese name, that is Chunhua Charlie, that is the American name, and for me it was really difficult to find Charlie at some point. And now I have a lot of help from Charlie with SMA. He was a really nice person and helped me a lot. Okay? Thank you, listeners. Thank you. And the next one is Masayuki. He's going to talk about this substructure in the Circumstellar.
You will come
Your
here.
own computer. Okay, great. Okay, thank you. So first of all, I'm Yamaguchi, working as a postdoc at ASIAA. So in this morning, most of the presenter connection with I have no connection with you. Sorry. But thank you as inviting me as a presenter. Yeah. So I think this is the first time to contact with you. Yeah. So please remember me. Yeah. So I talk about our recent studies of the new insight of the substructure in the Taurus, where Circumstellar by using ALMA. So this the conference name is for growing the nuclear at higher resolution. So I believe that this content closely connected to my studies. So I hope that the radio astronomer will get involved in this the ALMA should be helpful for my studies. Okay, I hope it works. Okay, so I'm studying mainly focus on the gap structures of Circumstellar. So first of all, let me explain the required spatial resolution to detect the gap structure. So this central figure shows the required spatial resolution as a function of planet location in gap. So which is based on the theoretical relation on considering the Higgs radius of the planet. Basically, spatial resolution is proportional to the planetary mass or distance from the center of state. So if gap is formed by the Neptune mass planet, orbiting at a distance of 15 AU around the solar mass scale, imagine with the resolutions better than 0.05 arc-second is necessary to detect the gap structures. So what I want to emphasize is that the resolution better than 0.05 or the 1 arc-second is play a crucial role in investigating the cyclical property of the gap. So, okay, from now, let me focus on our target. So this figure shows gallery of crusted water-lake disk in Taurus-Auriga regions. So those images were taken by the unphysics collaborative data set with the conventional green imaging techniques. What we can see is some of the disks show the uneven and gap structures around host scale. Yeah, most of disks has not clear gap link structures on the images. So this is mainly because there has been observed with insufficient spatial resolution relative from the 0.1 to the 0.2 arc-second. So it is likely that some structure should exist in the disk. So the current issue raises questions. So can we identify any statistical trend of gas properties by improving the spatial resolution to better than the 0.1 arc-second? Okay. So here, let me focus on the imaging techniques. So some of the anomalies maybe know that the clean algorithm has established itself as the most reliable method for the reconstructing image. But it has limitations of the spatial resolution due to the conversion of the clean model with the synthesized beam. Yeah. This conclusion behaves as robust filters and consider also the high resolution information of the observability data. So here is our strategies to overcome the limitation of the spatial resolution of the ALMA data by using the new imaging techniques with Protostars. So this is one of the techniques developed by the researcher who enabled to obtain the high resolution and high volume image of the black hole shadow with the electron telescope. So I think that the researcher who get involved in this electron telescope knows its equations. So this technique can directly solve the incomplete sampling of the observable data
by using non-parametric imaging, consisted of the wave class here plus the 2 penalty times L1 and his photospheric applications. So due to the limitation, I will skip this term in details. Sorry. Okay, in our previous series, we established a reliability of the reconstructed disk structure by using disk imaging techniques, as demonstrated in the bottom figures. In this work, so we use two datasets taken by ALMA to assess disk performance. So one acquired with a low resolution data and the other with a high resolution data. So our target is well known to study the disk of the 142.727. So this special resolution of two data sets is different from factor of 3. Yes, enrolling is already on our imaging process. We successfully validated this super resolution image taken from the low resolution data is consistent with the reference image. Yes, of the high resolution data within 10% error. So after successfully applying our imaging techniques, we developed the new imaging software called Astrophysics. So this software can do the same imaging with as we do, as long as you have a measurement set of ALMA data set. So this imaging process takes place in the constant environment and have a computing time compatible to the data of the current imaging. Yeah, in our study, we use this the software to improve the spatial resolution of those disks while maintaining the image quality. Okay. So, right figure shows the gallery of images with our imaging techniques. Here, as we know, eventually, so we confirm that the submarine achieves the spatial resolution compared to the achieves the better spatial resolutions compared to the conventional imaging techniques of the green by a factor of 2. So most of the reconstruction resolution are better than 0.1 arc second. With the highest resolution achieved in 0.02 arc second. Right. Interestingly, we found that there is a gap ring in the northern half of those disks. Okay, so from now, in order to investigate the statistical trend of the gap properties, so we extract the gap width and depth from all disks. From the azimuthally average linear intention profile converted from the image. So depth of the gap, depth and the width of the gap can be measured. So by using the only special resolved gap properties for the first time, we found that the relation between the width and depth of the gap on the right figures. So interestingly, we found that there is a robust scaling relations of the gap width and depth with on this with a robust strong correlation coefficient of 0.8. So as you know that there are several mechanisms proposed to explain the origin of the gap structures, such as hydrodynamic chemical process and plant-based interactions. So in those mechanisms, there is only theoretical relations for the primary origin model obtained from the numerical simulations. So this theoretical relation has a power law function of gap depth, as you can see here. So when we apply this scaling relation on the left figure, so we found that both observation and knowledge shows a remarkable consistency. Okay, but in this case, so we found that the outlier sample with wider gap deviated from the model because the gap too widely opened. The plausible hypothesis is that the giant planet embedded within the disk often wide gap through the parallel interactions. This scenario can induce a significant deviation related with estimating their primary mass when within the model. So particularly when a spherical European mass planet creates a wide gap. So we pointed out determining their primary mass with a wide opening gap with the model could generate a large asymptotically. In another case, so we also found that two adjacent gap in the AA tau disk and show the deviation from the model due to their narrow gap width. So as one of the possible explanations based on this structure, this deviation could stem from the presence of super Earths formed with a very low viscosity. So this is possible because the lowest planet can generate narrow gap with gap width through their propagation of the spiral density waves. And finally, here, we confirm that the 11 gap mass molecular duration is beautiful. So majority of them are from their outer region beyond the radius of 30 AU. So given the agreement between the entropy of the disk and those expected from the point disk interaction model, so we estimate the infinite planet mass by using the empirical method based on the planet interaction model. So our estimate suggests that the majority of those gaps are likely host of Neptune Jovian planet located beyond 10 human billions. Yeah, it's interesting. It's also likely that primary mass tend to degrees of large radius. So this trend consistent with the result obtained from the each of these, which primarily focus on the big bright and large disk. Okay, so in 2 minutes, so from this slide, let me discuss with a possible scenario of the prime location, prime homage and large orbital separations. So here we consider the combination of the small phenomenon and the subsequent gravitation and secondary gravitation instabilities offer these explanations. So in this initial crossover phases, the active outflow is driven by the magnetic field entering the ground dust, and thus reside in the inner regions of the embedded disk. And this is called as the Ashford phenomenon. Afterwards, the dust ejected from the outflow back to the envelope located at a distance of 1,000 AU from the central sphere. It is like a broken here. So once the protostars disk can be replenished with a ground dust that accumulated from the envelope. In practice, the presence of ground dust in the protostar envelope has been suggested by the previous observations. So the specular index of the dust opacity in the envelope of the some cluster 1 object is lower than that of the interstellar media interest. So which may be detected elements of ground dust right from the outflow. Okay, so and then so the difference dust creates good condition for the growth of the secular gravity instabilities. So this mechanism has the capacity to generate secular gravitational instabilities. So it's a structure within the disk, which enable to formation of the dust condensation within the rings even after large orbital separations. So it is likely that this mechanism operates during the area cluster 1 phases, as shown in the edge at the top. Okay, so let's slide. This dust condensation may grow near the evaporation until the reach for isolation mass with the cluster class 1-2 phases. So once the core mass exceeds this threshold, the flight acquires glass envelope through the non-aware regions. Yeah, so this result in the formation of the giant current just creates a right gap and become one of the bulk with a level segment of the point embedded in the disk. So this argument is compatible with our research because our estimate of the quantum glass exceeds the paper isolation loss. And we also found that presence of envelope element in the cross-two disk by comparing the defined spatial scale, such as ALMA and the 30 megapascal. So this envelope element has 20% of the disk total drugs, which suggests that there is still the Japan mass brand exists. Okay. Okay, so let me summarize everything. Okay, this is fine. Thank you for attention.
Yeah, so I have a question about your response model. Yeah, so I was just wondering, we always use a different weighting in a clean algorithm, solvable box.
Yeah.
And then we often use something like 0 or minus 0.5 or whatever. But we don't seldom go to like a -2, and 2 gets the highest possible resolution. So when you compare your model with such a model with a robust -2, do you see the difference?
So that's image created for the spot modeling image is better than the green with a robust -2 because when reconstructing the image with the green of the robustness -2, there the strong noise should be arise around the source area. But spot modeling does not arise such a strong emissions. And because spot modeling can reconstruct the image without the being convolutions, like brains. So this is one of the advantages of spot modeling imaging compared with the Kuan algorithm.
Thank you. I think we are not. Let's take again to all the participants. Thank you.